2.5 is a continuation of what we did last time. Last time we started factoring polynomials, and there's really nothing special about splitting these two sections up except that it's a lot of material for one section, so we've kind of cut it in half. So this will pick up where we left off last time. Last time, one of the things that we were looking for in a lot of the problems we did were greatest common factors. Do you guys remember that? That was like the one, Anya, that you were asking about at the very beginning where you didn't even have to factor everything out. It just said, what's the greatest common factor? So when we're looking for factoring, we will start with that piece, looking for a greatest common factor. Sometimes there is something there that's not just one. Sometimes there isn't. It just depends. But we'll look for a greatest common factor. And then step 2 is that we're going to either use trial and error or the AC method. Have I talked about either of those methods yet? I believe we did last time, right? So we talked about the fact that the AC method is really great. It doesn't seem real maybe useful when we were doing this section before because all of our A values, our coefficients, relating coefficients of 1, well, today they won't be. So you'll actually see where that comes into play and how that can be used today. I do realize that there are other methods for finding factoring. If you have other methods that you can use and you can use them effectively, that's okay. But these are the two methods that I think are the most useful that I'm going to present from here. So your call on that. All right, so we're going to use trial and error in some places where I'm specifically wanting to make sure you see it used. And then we're going to use the AC method specifically in some methods. So on these first two, I want to do factoring with trial and error. Now, no matter which method I use, I'm still going to do the looking for a greatest common factor first. So when you look at problem number 1, 5y squared minus 45y and plus 90. Is there any number, besides 1, because that always happens, but any other number that divides all of the terms? 5 does. That's exactly right. Any variables that are present in all the terms? Y is in 2 of them, but not in the third one, right? So there's a constant at the end. I don't have a variable in all the terms. So I just have the number 5. So my first step is to pull the 5 out and then to divide each factor by 5. So 5y squared divided by 5 would be y squared. How about my 45? What would that one give me? 9. So I have negative 9y. And then how about 90 divided by 5? Anybody? 90 divided by 5. 18. It's 18, yes. Thank you. 18. Good. Okay, so that's the first step. We're going to factor out any greatest common factors that are present in all three pieces. After that, on these specific ones right now, we're going to use trial and error. So trial and error means that I'm going to set up 2 sets of parentheses. I need 2 numbers that give me y squared, so that's y and y. And then I need 2 numbers, let me pause for a second. I need 2 numbers that will be the same sign because I'm supposed to get a positive when I multiply them at the end, so the signs have to match. And this middle sign tells me they both have to be negative. So I'm going to have a negative and a negative. I need 2 numbers that multiply to 18 and add to 9. What would that be? Multiply to 18, add to 9. Okay, how about some multiplies of 18s? I can do 18 and 1. What else can I do? 2 numbers that multiply to 18. 2 and 9, good. What else? 3 and 6. And I think that we're done at that point, right? These are the only options. I need to choose the 2 that add to 9. Which 2 are those? Yeah, the 3 and the 6. So there will be a 3 here and a 6 here. And you can confirm to make sure that it works, of course, if you take, use the red, if you take these 2, do they multiply to give you positive 18? Yes, right? And then if you look at the inside and the outside, do they add to negative 9y? Yes, they do. So this is the correct factoring for this one using trial and error. Okay, taking a look at number 2. Starting with the idea of greatest common factors. Is there any number or variable that divides every single term? besides 1? There's not. There's not a greatest common factor here. So I'm just going to sort of jot that down to the side that you look, so that when you look back, you'll remember that we checked for it and there simply wasn't one. But we should still be checking for them every time. There just isn't one. So we're going to do trial and error on this one, and it's going to be a little bit more challenging because there's a 3 at the beginning, right? So in order to get 3x squared, I would have to have 3x and I would have to have x. If you want to write it as 3x first and x second, you can do that, or we could have written it the other way, and it would be just fine. The important part is that I have a 3x in one place and an x in another place, so I end up with 3x squared if I were to try to multiply them. Okay, we're going to look at the signs then again, just like on the last one. The two signs have to be the same in order for me to get a positive at the end, and they have to be a negative because there's a negative in the middle. So my signs will both match, and they will be negative. So by number 8 now, I can get an 8 by doing 8 and 1. How else could I get the number 8 if I multiply two numbers together? 2 and 4. So this isn't a terribly awful one because there aren't a ton of options that I can multiply together to get 8. Agreed? Okay, there's really, this is actually one of the nicest options, if you will, if you're going to use trial and error, because I don't have a lot of options. 3x and x gives me 3x squared. I don't have any choices there, right? The signs both have to be negative. I don't have any choices there. The values at the end are the only thing that could be manipulated and have different choices. I have 8 and 1 or I have 2 and 4. So there's actually 4 different things I could do. I could do 1 and 8. I could do 8 and 1. I could do 2 and 4, or I can do 4 and 2. There's 4 choices. Sometimes you're fortunate and it's the very first one you try and you're done and it's great. Sometimes it's the last of the 4 choices you try and you're like, man, it took me all 4 choices to get to the right one. Okay, that's what trial and error does. Sometimes it works efficiently and very quickly, and sometimes it doesn't work so very efficiently and it's the very last one. So somebody give me which one you would like to try. Do you want to try 8 and 1, 1 and 8, 2 and 4, or 4 and 2? 2 and 4. Is that what I heard? Let's give it a go. 2 and 4. So if we try 2 and 4, we know we get the 8 at the end. The concern is going to be, do I get the right number in the middle? So right here I have negative 2x in the middle. And right here I have negative, 12x. So was that you, Cole, that said that? Or Elijah? It was Elijah? Okay, I was like, it's from this corner. So you picked well, didn't you? Because what's negative 12x and negative 2x? Negative 14x. So that was an awesome pick. It was a really good first try because it actually worked. If it didn't, you'd erase the 2 and the 4 and you'd choose another option. Usually I stick with the same numbers and just flip them as my second option, whatever I've chosen. And if that works, great. And if it doesn't, then I switch numbers. Just that I'm trying to, organized guess going through all my options. Okay, is everybody good with that? I'd like to draw your attention to something that occasionally will happen when we have problems like this. Sometimes people want to then set things equal to 0 and start solving. These aren't equations. They're not equal to anything. They're just expressions that you're told to factor. So be really careful that you're not doing sort of more than what you're asked to do on any particular problem. This isn't a solving problem. It's just factoring. Okay? All right, we have a couple more. And we'll go back and we'll do some of these problems with the AC method in a minute. But the directions stay the same for now. I am supposed to factor completely using trial and error. I start out with greatest common factor. 7x squared minus 5x plus 2. Do they have anything in common to all 3 terms? Nope, there's no GCF on this one. So again, I'm just going to jot it down so that hopefully if you look back at these and you're like, wait a minute, we didn't do that, you'll know that we did. We checked it. It just didn't have anything. Okay, so with trial and error, I have 2 sets of parentheses. Again, in some sense, this is nice because 7's a prime number. I can't get 7x except by doing 7 and 1, right? 7x and 1x. So I don't have choices. And it doesn't matter whether you put the 7x first or the x first. It doesn't make any difference. Now, I do have a choice on the negative sign. So there's a negative sign at my ending term. In order to get 2 numbers that multiply to be negative, one of them has to be negative and one of them has to be positive, right? So I actually, at this point, have some flexibility, and I may choose wrong. So maybe I do a negative here and a positive here. That's an option, but I also might have picked the wrong order. Okay, so this is one thing to do. Then I have actually a fairly nice option here at the end, the number 2. The number 2 is only 2 and 1, right? Those are the only things that have the ability of working. So there's actually still 4 things potentially that could happen here, right? One option is that I put my signs in the right place, and I could put a 1 and a 2 or a 2 and a 1. The other option is my signs are in the wrong place. And if my signs are in the wrong place, then I actually would have to change the signs and still have the option of a 2 and a 1 and a 1 and a 2. So there's still 4 choices. Even though my numbers are a little bit nicer than the last one, my signs are a little bit less friendly. So we're going to stick with the options where I've got a negative and then a positive for the moment, and we're going to pick, do you want to do 1 and 2 or 2 and 1? Somebody give me a choice. 2 and 1. All right. So we're going to do a 2 here and a 1 here. And again, we know by our choice of things that the number will multiply to negative 2 at the end, and it does. The concern, what we're wanting to always check, is that the inside and the outside add to the right value. So we're going to check that. So on the inside, that's negative 2x. On the outside, that's positive 7x. So if I take negative 2x and I take positive 7x, what will that give me? 5x. 5x is what I have in the middle, almost, right? So I have the right numerical value, as in like the 5 itself, but I have the wrong sign. Agreed? So when that happens, it's actually very nice, because what that means is that the numbers are all in the right place. I just need to switch the signs that are happening. So instead of this being a negative and then a positive, it should have been a positive and then a negative. And if I redo that in the right order now, there would be a positive 2, there would be a negative 7. Positive 2 and negative 7 give me, in fact, the negative 5 that I was trying to get in the middle instead. So I picked sort of the location of my 2 and my 1 right, but I didn't pick the signs correctly. And I can adjust that very quickly when I realize that the sign's just wrong on my middle term. How about number 4? Any greatest common factor there? No. You might feel like, well, there's just not a greatest common factor most of the time. And the answer is, well, that does happen a lot of the time. But I'm telling you what, if you don't check for it and there's one there, you're going to be trying a lot of things before things are going to work out very well for you. So it's definitely still something to check beforehand. Okay, trial and error. So, one thing I wanted to notice on this one. Do you notice what's different about this one than the last ones we've done? The first one's negative. That's a very good observation, Cole, and it's really important. It isn't that we can't work with the first one being negative, but I'll tell you right now that it's definitely a hassle to have the term in the front negative, okay? So while there isn't a greatest common factor that's not 1, I do want to factor out that negative that's at the beginning to make it easier to do trial and error with. It'll also be easier if we were doing the AC method. So the first thing I really would like to do is pull the negative out. And if I do that, it changes all my signs. Again, if you leave it in, will it work? It will. You can work with it. It's just kind of awkward and ugly. It's easier to work with a positive first coefficient. Okay? So we're going to take the first negative out, or the negative out of all the terms first. Okay, so we've got my negative out. So you could kind of say, if you prefer, you can write this as a negative 1 at the front. If it bothers you to just leave the negative there, you can write it as negative 1. Okay, so what remains then is the trial and error step. So we'll do our 2 sets of parentheses. We've had a 3 before. 3 is kind of friendly because it just means I have 3 with a variable and then 1 with a variable, so 3W and W. Okay, I have a negative here at the end. I feel like that orange is not very bright today. Let's see if the yellow will be brighter. Is that any better? Yes? Okay, we'll go with it. All right, so I have a negative at the end. What does that negative tell me I need to do about my signs? We had one just like this. Huh? Do they both need to be negative or just one of them, though?
Just
Just one. So I do need a negative, but I need just one to be negative. And the reason, again, is because in order to get the two numbers at the end to multiply and be negative, I need one positive and one negative for that to happen. And again, I may have put them in the wrong place. I didn't even look. I put them in the wrong place on purpose last time, just so you know. I wanted you to see what happened. I'm not looking. So we're just going to see what happens this time altogether. Brand new experience, okay? Cool. All right, so we may have to switch our signs later. We did it once before, so I think we can handle doing it again. All right, my 4 at the end. What two numbers multiply to give me 4? Give me something. 2 and 2. What else? 1 and 4. So I actually have two options. We get to pick which one we would like to try. Would you like to try 2 and 2 or 1 and 4? 1 and 4. And I said 1 and 4, so I'll just write it as 1 and 4, and we may need to switch it and make it 4 and 1 too. Like that may be a choice, right? The check. So what we're checking is that the middle and the outside give me what I would want, and I don't know. We're going to check. So in the middle right now, I have negative 1w, and on the outside, I have 12w. What is negative 1w plus 12w? 11w. And is that my middle term? No. So this is not correct. So my first thing that I would suggest that we do then is to change the order of the numbers. Just switch the 1 and the 4 and check if that works. If it doesn't, then I know 1 and 4 are simply not the numbers I want to use at all. So we're going to try these two. So in the middle now I have negative 4w. On the outside I have 3w. What does that add to? Negative 1w. Is that middle term? Not my middle term. So we're back to fixing those. But what that actually did is it eliminated this as an option. It is not 1 and 4 in either order. And it won't matter if I change the signs. That won't help either, okay? Because if it were signs that were wrong, I'd get the right number, wrong value, and that didn't happen. So now we're going to try 2 and 2. Now, the interesting thing here is that I can't really switch 2 and 2 because it doesn't change anything. So this is my last option, really, except for that my signs might be wrong. In the middle, I have negative 2w. On the outside, I have 6w. What's that one give me? 4w. And that's exactly what I have in the middle term right there, right? So this is actually what I wanted. I don't need all this here if I haven't taken them off each time, but if you want to be real clear as you're making your answer choices, you can box them in or whatever, but this is actually my factored form. Now let's say, for instance, that you dealt with the negative and you never pulled it out. Your answer at the end might look a little bit different. It might instead look like negative 3w plus 2 times w plus 2. It might look like that, and it would be an acceptable answer. There'd be nothing wrong with that. That would be okay. Or instead, it might look like the 3w minus 2, and it might look like minus a negative w and minus 2. I'd be okay with that as well, all right? So there's actually 3 different, they look distinctly different, right? Answers that are all sort of equally acceptable on this particular problem, depending on how you deal with it. But it's harder to work with it to get those last 2 answers than the way we did it. All right, we're going to try a couple of the examples that we did. In particular, it was problems number 2 and number 3 with the AC method. So I've just rewritten them here. The number 2 and number 3, neither one had greatest common factors. Okay, so I don't need to worry about that piece. I'm going to show you what it looks like to do the AC method with these, though, instead of trial and error. So trial and error has sort of this nice, elimination process to it. I kind of like trial and error. But if you have a lot of things to try, it can sometimes be very tedious, and it can sometimes not lead to the solution very quickly. It can happen. And so the AC method is very nice because it doesn't have that. It's always going to work out, sort of routinely, step by step, the same way. So let's take a look at what we have for the AC method. For the AC method, we would take A, which here is 3, times C, which is 8, and we would get 24. So far, so good? The B value is negative 14. So I need two numbers that multiply to 24 and add to negative 14. Notice the only way that's going to happen is that they have to both be negative, right? That's not going to work otherwise. So what are two numbers that multiply to 24 and add to 18 or to negative 14? What are my options for getting to 24? Let's start with that. Well, I can do 1 and 24, right? What else could I do? 2 and 12. What else could I do? 3 and, don't everybody speak at once? 8. There's one more. Somebody give me my last option. 4 and 6. Now we already said the signs have to match because I need to get a positive 24, right? So the fact that there's a negative here means again that my signs have to all be negative. So I really have negative 1 and negative 24, negative 2 and negative 14, negative 3 and negative 8, negative 4 and negative 6. Which of those options, there are 4 of them, will give me negative 14? Yep, negative 2 and negative 14. Or negative 2 and negative 12. I don't know why that says 14. I think I just typed it wrong. So sorry. That's what I meant to say. Negative 2 and negative 12, yes. Okay, everybody good so far? So this is like the scratch work on the side. I'm going to shift it over just a little bit to give myself a little more space, and I'll delete it in a moment. So working through this right here, I need to leave the 3x squared the same. And instead of writing negative 14x in the middle, it doesn't matter the order, I'm going to write a negative 2x and a negative 12x. I'm just replacing negative 14x with something equivalent to it. Negative 2x and negative 12x are equivalent when added together to negative 14x. And then I have my plus 8 on the end. Is everybody okay so far? Okay. Again, if you switched them in the middle and you put your negative 12 first and your negative 2 second, it'd be okay and it'll work out. So don't fret about that. Just pick one and go with it. So we're going to do these pairwise. Looking at the first two, 3x squared and negative 2x. What is a factor that they both have, the biggest thing that they have in common? X. Yeah. And if I take an x out, I'll have 3x left and minus 2. Is everybody good with that? Good. Now the last pieces are a little tricky. Let's just think about the numbers 12 and 8 for a moment. What do 12 and 8 both divide by? 2. Anything bigger? 4. Both divide by 4. Now if I simply take out a 4, I want to show you what will happen. Don't write this down necessarily, but if I take out a 4, I have negative 3x plus 2. And the problem is that's not quite the same as the other parenthesis, right? How is it different? Yeah, the signs are different, right? In fact, both of the signs are different. Agreed? So instead of doing it as negative 3x and positive 2, if I take out a negative 4, it'll change the signs as well. So if I took negative 12x and I divided by negative 4, I'd get that positive 3x. And if I took an 8 and I divided by negative 4, I'd get the negative 2, and then they would match. Okay, so we need to get those middle terms, the parts that are in parentheses, I mean to say, to match in order for the AC method to be done correctly. So now that these match, just like the question that you asked me, Gracie, at the beginning of the class from the last lesson, this looks like this now, right? So we factor out that 3x minus 2, and we notice we have an x and a minus 4 that are still remaining to finish out our problem. 3x minus 2 and x minus 4. Okay, so that's what the AC method would look like for that problem. We're going to try it again over here. So a times c, a is 7, and c is negative 2, means I get a negative 14. The b value in the middle is negative 5. So negative 14 only has two choices. It's 1 and 14 or what? Seven and 2. Thank you so much. And they both have, they have to give me a sign that's negative, right? Which means one of them needs to be positive, the other one needs to be negative. So I actually have four choices. Let me write them out just so you can see them. But I have negative 1 and 14, or I have 1 and negative 14. I have negative 7 and 2, or I have 2 and negative 7. Those are really the four choices that I actually have here. When the signs give me a negative for that A times C, I end up with more choices that I have to consider. And I need to pick the one of this four that gives me negative 5 when I add them together. So which one of these four will give me negative 5? The last one. Yep, 2 and negative 7 give me negative 5. So I will change my expression to say, still says 7x squared. And I'm just going to do it in the order that it's listed. So this is 2x and negative 7x. If you switch the order again, it doesn't matter. That's fine. It'll work out. And then I have minus 2. So again, all I'm doing is I'm rewriting the middle term, the b term, to be split into two pieces. And the pieces are chosen specifically to do something, right? But those two pieces, if I were to combine them back together, have to give me negative 5x to be the right split. And then we're going to factor by grouping. So I take the two pieces at the beginning and I say, what do they have in common? X. And if I take out an x, I'm left with 7x plus 2. Perfect. How about negative 7x and negative 2 at the end? What do they have in common? They don't have an x. We're looking at these pieces here at the end. What do they have in common? They're both negative, right? So on the last one, notice I factored out a negative 4 here, but my choice in doing so, the reason I did it was because the signs needed to be switched on the inside, right? Here I'm going to factor out the negative because they simply have a negative. Both of them have a negative, and I will pull out a negative, and if it helps you to see it, I'm going to write it as a negative 1 for the moment. So if I pull out the negative 1, I have 7x and plus 2. Notice they match. That was my goal. So that's good. I have matching 7x plus 2 on the terms. So now, just again like the last problem, I end up with a place where I pull out the parts that match, 7x plus 2. I factor them out. I'm left with an x, and I'm left with minus 1 for my other pieces of my factoring. Okay, so there's more structure with the AC method, which is interesting because normally I really like structure, and I like the AC method, but I kind of like the game sort of feel of the trial and error and process of elimination too. So it's your choice. In your problem sets, it will never tell you which way to do the problems. You can pick. It doesn't matter to me in the slightest. So whichever one you feel is most comfortable or you're the best at doing, pick that one and use it, okay? And if you feel like sometimes you like one method and the other methods on the other problems, you can do that as well. All right, any questions on the AC method or trial and error? Because we're about to shift gears a little bit. Okay, the last part that we're going to take a look at in this section are some special factoring forms. There are two specific forms that we're going to look at. One's called a perfect square trinomial, and the other one is called difference of squares. Perfect square trinomial is very useful when you do certain types of factoring. And it says the following. It says that if you have, actually let me do it this way, a squared plus 2ab plus b squared, and if it has that form to it, that this factors very nicely as a plus b times a plus b, or more compactly, a plus b quantity squared. Now, the reality for what we're doing is that if you encounter a problem like this, you can still use trial and error. You can still use your AC method. If you're familiar with another method called slide and divide, that's another method that you have at your disposal. If you aren't familiar with it, ignore that I just said it. It's fine. I'm not going to show it to you. You have choices. But if you happen to recognize that it's this perfect form, you have another option. It won't happen all that frequently, but when you notice it, it's kind of nice. So this is sort of one of those, it's not crucial at the moment to know it, but it fits in very nicely with our description here. The next one, you absolutely need this form because it doesn't work with all our other methods that we do things with very nicely. It just doesn't. And it's called difference of squares. And what it looks like is it looks like you have two terms squared and they are subtracted from one another. So it's not a trinomial at all, like the other ones that we've done today, right? I don't have a middle term. There is no, that bx in the middle kind of thing that was happening when we did the AC method. I don't have that middle part. So how does it factor? Well, it factors as a plus b times a minus b. And we have already seen this way back. I can't remember which section it was. I want to say like maybe 1.6 that we did before. We saw this when we worked with conjugates. Do you guys remember? We're trying to rationalize denominators and make it so that we didn't have any radicals on bottom. So maybe it was 110 actually then. I bet that's where it was. When we were trying to make it so that it didn't have any values on bottom, we multiplied by the conjugate and notice that that's exactly the relationship that we see here, right? They're conjugates of one another. And when they do that, they end up having the middle term cancel out. And again, the reason that happens is because this is positive AB and this is negative AB. And when I add positive AB and negative AB together, I get, don't leave me hanging, what do I get?
Negative AB times negative.
No, when I add them. Positive AB and negative AB give me 0. Yeah, I get nothing. That's why I don't get a middle term, is because of the way that these operate together. So we've got some examples where these two specific methods are working for us, or have the ability to anyway. Number 5. Now, if you're trying to decide if it's one of these two, you can very quickly decide which one you should be trying. The first one has a trinomial in it, and the second one is not. It's a binomial. So on this one, number 5, you see a trinomial, right? Yeah. If you notice here, u is being squared. What's being squared at the end? What's 81 if we take something squared? It's 9. 9 squared is 81. In the middle, you'll notice that this is actually 2 times that 9 and times the u. Again, if you don't notice these things on this problem, you can still do it with trial and error. You can still do it with the AC method, and it'll all be just fine. I'm just drawing your attention to the fact that this one has a very nice pattern to it as well that we don't always see. So if we notice this pattern, what it means that I can do is that it means I can factor this as u plus 9 times u plus 9. Or we can write it as u plus 9 squared. Because it fits the pattern of a perfect square trinomial. The first term is squared, the last term is squared, and the middle term is those two outer terms, the first and the last one, multiplied times 2. And that's what I have here. First term u is squared, last term 9 is squared. In the middle, I have 2 times 9. I'm sorry, in the middle I have u times 9 times my 2. So it is a perfect square trinomial. Number 6 and 7 clearly only have 2 terms, right? They're not perfect square trinomials because they aren't trinomials to begin with. They are, in fact, differences of squares, though. So the last term is clearly w that's being squared. What term squared is 25? 5, yeah. So this is 5 squared minus w squared. That's what this is really presented as. It's a difference of squares. So the difference of squares formula says one of the terms will be 5 minus w, and the other term will be 5 plus w. And if you wanted to check and make sure you were right, what could you do? What could you do to make sure this is right? You could expand it out. Yeah, if we multiplied this back out, first, outer, inner, last, distribution, all that good stuff, it should end up giving me 25 minus w squared. And it will. So you can always check your work on a factoring problem. And you can do it on any of the factoring problems that we did today, right? Every single one of them should multiply or distribute or expand back out to give you the original piece that you started with. Okay, 7's a little bit different. It doesn't look quite as clean because it have a 25 and a y squared both sort of at the beginning, right? But what I want to do is I want to write it instead in such a way that I can actually square it and still have 25y squared. So what squared is 25? 5. We just did that. So this is actually the same as having 5 and y in parentheses squared. Because 5 squared is 25, y squared is y squared, so 25y squared is what I would get on this. How about 49? How do I get it to be something squared? 7. So 7 squared. So in a very real way, my a value is 5y and my b value is actually 7. Those are the pieces individually that are being squared. So we would do 5y minus 7 and 5y plus 7. Is that okay? All right, my last two examples combine more than one thing of what we've done today into a single problem. You'll notice on all three of these, I failed to say it, but that's actually a true statement. There was no greatest common factor on any of them, right? We didn't have that. We failed to check it, but they didn't have it, so it didn't much matter. On number 8, there is common factors. And if I don't notice it and I start to try to work with it, I'm going to run into some really hard problems. It's going to be very challenging. So taking a look at what's there, I have 3u to the 7th minus 30u to the 6th plus 75u to the 5th. And I need to know what they have in common. And we can do it component-wise. We can look at the numbers and say, well, what number divides them all? And then we can look at the variables and say, what variable divides them all? Okay? So what number can I factor out of all three of those coefficients? 3. So I'm going to do that. Now I need to look at the variables. I have u to the 7th, u to the 6th, and u to the 5th. What do they all have in common? U to the what? U to the 5th. Right, u to the 7th means I have 7 u's, so there's at least 5 of them. U to the 6th means I have 6 u's, there's at least 5 of them, and u to the 5 is 5 u's. So if I take 3u to the 5th out of 3u to the 7th, what am I left with? U squared. If I take 3u to the 5th out of negative 30u to the 6th, what am I left with? Negative, not 6u. I'll have a u, but it's not a 6. It's a 10, yeah. So negative 10u. If I take a u to the 5th out of the last piece, there is no u to the 5th at all anymore. But what about the 75? What's 75 divided by 3? 25. Think about like 75 cents. It's 3/4, right? Okay. Now, if you happen to notice, this actually is a perfect square trinomial. The first term is squared, it's u squared. The last term, 25, is squared, it's 5 squared. In the middle, I have the 5 times the u and so forth. But you also might not notice it. So I'm going to pretend like you didn't notice it because I think it's probably something that most of the time you're just not going to pick up on a particular problem. So you can choose. You can do it if you notice it. It's perfect square trinomial, great. You can choose the AC method, that's great. You can choose trial and error, that's great. I'm going to do trial and error on this one. I think this one works pretty nicely with trial and error. And again, part of the reason why is because the a value at the beginning is a 1. I don't have a coefficient now anymore in front of my u, so I just have u and u. Okay. The sign at the end is positive, which means the signs have to match. The sign in the middle is negative, which means the matching signs are negatives. Now I need two numbers that multiply to 25 and add to 10. 5 and 5. Also another reason it's so friendly looking. You can read it like this, leave it like this, or you could, if you wanted to write it this way, it is 3u to the, that should say, I don't know why that says squared, I'm so sorry, that should say fifth still. 3u to the fifth, it didn't change, shouldn't change, 3u to the fifth. And you could write it as u minus 5 squared if you wished. There's no reason to do it that I need you to, I just want you to recognize that if you did, it would be okay. Okay? That's why it's perfect square trinomial. Do you see that now? These two pieces match. How about the last one? Number 9. 6y to the fourth, 20y cubed, 14y squared. Let's start with the numbers. Do they have a number in common to all three pieces? Yeah, 2. Is there a variable common to all three pieces? Y squared. So we'll first take a 2y squared out of every term. So if I take 2y squared out of 6y to the fourth, what am I left with? 3. How many y's? 2 of them, so y squared, right? 20y cubed. Well, if I take a 2 out of a 20, I'm left with a 10, thank you. And if I take y squared out of y cubed, I'm left with y. The last one, 14y squared. Well, the y squared is going to be completely removed, right? So if I take the 14 now and I divide by 2, what am I left with? 7. This is definitely not a perfect square trinomial like the last one was. You certainly could use trial and error if you wish. I'd like to show you one more time the AC method, just so you can see it be used in the middle of problems like these. If that's your preference, you can do that. Otherwise, you're welcome to do trial and error instead. The 2y squared at the beginning, actually, let me just not write it for the moment, is going to remain. It's still going to be part of my answer. But I'm mostly concerned at the moment with factoring this piece in the middle with the AC method. So AC, A is 3, and C is 7. The B value in the middle is 10. So 7 times 3 is actually 21. Now 21 doesn't have a lot of options, right? It's either the 7 and the 3 that I just used, or it's a 21 and it's a 1. And my signs are all positive here, so everything's going to have positive signs. There are no negatives to worry with, so everything's positive. I need the 2 that will actually add together to be 10, and that would be 7 and 3, right? So as I'm looking at rewriting, this middle step, would be the 3y squared, and then the 10y that's in the middle will be written as 3y plus 7y in either order, and then plus my 7 at the end. And again, I still have that 2y squared at the beginning. Pieces at a time, 3y squared plus 3y. What do they have in common? 3. And y. Yeah, 3y. So if I take a 3y squared, I'm going to put a bracket here just to separate it from my 2y to the squared, y squared at the beginning. If I take a 3y out of the part that's highlighted in yellow at the moment, well, 3y taken out of 3y squared is, what do I have left? A y. And if I take a 3y out of the 3y that's here, what am I left with? 1. So it's really common that people want to say, well, I'm not left with anything, but I am. Remember, it's division. Factoring is equivalent to division when I'm pulling these factors out in front. So I'm left with a value of 1. How about 7y and 7? What can I take out of both of those? 7, which leaves me with the same y plus 1, right, that I had on the other term. So I've got that 2y squared in front. Now I have the y plus 1s that match. So I'll pull out my y plus 1. And what will that leave me with?
3y plus 7.
Yep, 3y and positive 7. So 3y plus 7. And again, the order of the factors doesn't matter. So if you had 2y squared at the beginning and you actually had the y plus 1 at the end with the 3y plus 7 in the middle, that'd be fine. It wouldn't make any difference at all. If you don't want to use AC method in the middle of this and you want to go back to using trial and error, fabulous. Go for it. Any questions on that one? Okay, I think that you will find the factoring a little bit more challenging this time. We have a lot more going on than we had in our last lesson. So go ahead and grab out your homework or grab your phone. There's 24 of them. And let's start taking a look at the factoring that we have in this section. And I'll be coming around to help as you have questions.